Okay, YouTube, in my last video we discussed how to write the simplest form, or at least reduce a rational expression to its simplest form. In this video we're going to talk about how we actually multiply fractions. And so basically what we're going to have here are rational expressions, or a couple of ratios in which we have algebraic expressions in the numerator and denominator instead of just numerical values. So the way we're going to treat this is the same way we treat numerical values, which is if you multiply two fractions we often just do it straight across. So we would say that the product of ABS over times CDS, or ABS of CDS, would be AC over BD. So using this fact here, what I'm going to encourage everybody to do when we multiply rational expressions to find their products is to, first things first, before you do anything, is factor all rational expressions. We'll write this down. Factor all rational expressions in the product. And this means both the numerator and the denominator. We want to make sure we know that they're both the num and denom. Okay. So that being noted there, we want both of those things factored. I will look at this first rational expression. We'll talk about how we could do this. First things first, we could just go ahead and multiply this straight across. And actually I'm going to do this. I say 5 times 6. This would give us 30, and we say x squared times x to the third. When you multiply two things with the same basis, remember that you add their exponents. So we'd say 5 total x's, we have 3 total y's here in this product. And then in the basement here, we have 2 times 10 is 20. X to the first times x to the 0 is x to the first, and then y cubed times y to the first is y to the fourth. The thing here is this. When you look at this, we would say that this is not in simplest form. Basically, it's the answer, it's the product, but it's a really hyperinflated answer. So just like I would if I had something like 2/3 times 6 ninths, just like I would say, well, 6 and 3 cross reduce, and I would get 1 and 2. And I would say, well, 2 and 9 don't cross reduce, 2 and 9 here don't cross reduce, and 2 and 1 don't cross reduce. And then I would multiply it and get something like 4/9. The thing here is, with this, I could guarantee it's in simplest form because we did all our reducing first. So what we've done here is we've found the product, but it's really got a lot of reduction to have done. As a matter of fact, 30 over 20, we would say that 10 goes into both of these. This would be a 3 and a 2. So we would end up with 3 halves. And then we'd say x to the fifth over x to the first. We would say that's really x to the fourth here. So we say x to the fourth. And then last but not least, we say, well, y to the third over y to the fourth. These 3 cancel out with one of those, or 4 of those, and leave one of these behind. So we say like this, or we could say 3x to the fourth over 2y. Okay, so I want to come back to this because basically what you see over here, what I want to indicate is that we could cross reduce here just like we cross-reduce with numerical values. So what I'm looking at here is a situation where this, if we would have just reduced everything beforehand, we would have been in better shape. So I noticed that my 5 and my 10. 5 goes into both of those, so this would become a 1 and this would become a 2. And we would say, well, this 6 and this 2 here, I would say this would become a 1 and this would become a 3. Okay, so here's our 3 over 2 scheme, and I noticed that if I have x squared here and an x here, I could say one of these cancels out with one of these and I get left with x to the first here. And then I could say, well, this y cancels out with one of these y's down here, I get left with y squared over here. Over here we'd say, okay, well, I've got x to the first, y squared down here. I guess this y squared here would cancel out with this y squared here. So now what we're left with, it's kind of hard to see. And I'll tell you what, this comes in a lot more handy in the next expression or set of expressions here. But it looks like we got left with our, let's see, 3 x to the fourth. We have our x to the first and our x cubed, so 3x to the fourth, and then a y in the basement, and our 2 as well. Forgot to put a box around that. So let's look at these next couple of examples here. Essentially, and I'm going to have to, let's look, copy and paste it looks like here. We want this guy, C. We'll throw this one in. Oops. This is the example that we want here, so we'll delete this guy out. Throw this in, but let's look at example number 3 up here. Essentially, you see an expression where, I've got something times something and it's just fractions. What we're going to want to do is, of course, multiply these straight across. But as I mentioned on the last one, what we want to do is first factor both sides. So let's see if I can draw here. Cool. We want to factor this top expression here. I noticed that 4x and 4x squared have a 4x in common. So we'll factor out their GCFs. And we say 1 minus, and this would just have a single x on it now. We could check this by redistributing. So here's our top numerator here. I notice this is a trinomial. 2 factors of -3 that multiply out to be a positive 2, well, that'd have to be a positive 3 and a negative 1. So we'd have x plus 3 and x minus 1. So we're taking all of that times now. This is a trinomial as well. 2 factors of a -6 that add up to be a positive 1 would have to be x plus 3 x minus 2, and we would say that this is just 4x, and we could even say that it's like 2 times 2 times x, but we'd say now everything is factored. So when we started this, keep in mind, we are saying that all of these things are in the numerator and the denominator. We want to factor these out as much as possible. So I noticed some things here. First things first, these 4x's, they cancel out. And I also know that x plus 3 here and the x plus 3 here cancel out. There's about one other thing that I want to say about this, and this is kind of algebraic sneakiness here, but if you were to take this entire set of parentheses here times a negative 1, you could flip this order around and it would cancel out with this right here, okay? It would cancel out with this. So basically we could say that 1 minus x is the same thing as negative 1 times x minus 1. And I am going to write this because what I notice is that that x minus 1 and that x minus 1 would cancel out, and we'd be left with just and it'd be the negative 1 here. So we get negative 1 up here, just 1's down here, 1 down here, and the only thing left up here was really this x minus 2. So we get negative 1 times x minus 2. The simplest form of this expression would be negative times, or negative 1 times x minus 2 if we multiply this straight across, and then 1 times 1 in the basement would just be 1. So we get this, or we could even say distributing that we get 2 minus x. Bottom line though is we would say that this is the simplest form of this product, okay? So our goal here is to factor first, then cancel things out, then multiply, and list our simplest form answer. So let's take a look at this last one here. Again, we want to multiply these instead of just multiplying now and reducing later, which would give us really long expressions, okay? What we want to do is factor now. So I notice like this is sticking out in my head here. This is a difference of squares. So if we were going to rewrite this here, I would say this is x plus 3. I'll come back and deal with this here in a second. This is a difference of cubes. We'd say that I can't really factor the 2x minus 1 here any more than it is. I'm going to write that as actually a parenthetical quantity. And we say, though, that this is what I'm mentioning as a difference of squares. So this would be x, let's do this, x plus 3, x minus 3. And we'd say that 8x cubed minus 1. Now I notice this is a difference of cubes. And I'm going to write this here. We say a cubed minus b cubed. Its pattern is that we do a minus b. The things we would cube to get these two terms here, like 8x cubed, I would cube 2x. That's what I'd put here. And what would I cube to get a 1? Well, I could cube 1 to get 1. So this would be a 1, or will be a 1. But you'd say that it's just those two numbers in a difference with each other just because that's a difference. And then we had a times itself. This is going to be opposite this first sign here. So if this is negative, this is plus. We get a times b. And then this last one here is always positive when we say b squared. And so I will write this down since we're at it. We'd say this would be a plus b. And we get a squared minus ab plus b squared. But anyways, in this instance here, we have a difference of two cubes. So we're going to say it's a binomial times a trinomial. These are pretty easy to put together because you'd say I'd take 2x times itself 3 times to get 8x cubed. I would take a 1 times itself 3 times to get the 1 here. And this is a difference. So this will be plus, and this is always plus. And we would get 2x times 2x, which is 4x squared. We would get 2x times 1, which is 2x. And we would get 1 times 1, which is 1. So what I want to notice here are a few things. I would say that the x plus 3's, they cancel out. And our 2x minus 1, they cancel out. Okay. So what we get left with here is essentially we got 1's up here. We had 1 times 1 on top. So we get 1 over, now we get 4x squared plus 2x plus 1. All of that times x minus 3. And we would say that, this is probably the way you want to leave it. But this would be simplest form because I notice the top and the bottom share no other common factors besides 1. And I know because of the laws of differences in sums of cubes that this is not a factorable thing. So this would be the simplest form, and that's how you would carry out rational function multiplication. Cheers.